Section 5.5 alternating series. So there's a couple more definitions and tests to figure out if something converges or diverges in this section. So let's start off thinking about a series that alternates between positive and negative terms. In the previous couple of sections, like the comparison test, the integral test, and the divergence test, things had to be only positive. So here, let's consider positive alternating between positive and negative terms. How could we know something like that converges or diverges? So let's look at an example. So the first example would be the alternating harmonic series. If I started off with plugging in n equals 1, this would become -1 to the power of 1 plus 1. And 1 plus 1 is 2, and -1 squared is +1. And then over 1. Okay, and then plus. And then if I plugged in n equals 2, this would become an exponent of 3, which is a odd exponent, so -1 cubed stays negative. And then you can imagine that continuing on throughout the case. So I ended up with just like the alternating, just like the harmonic series, but alternating. So +1 minus 1/2, plus 1/3 minus 1/4, plus 1/5, etc. Now, without the alternating, when this was just a +1 on top, that was the harmonic series, which we know diverges, and we used the integral test to prove that the regular harmonic series diverged. So now let's look at the alternating harmonic series partial sums. So let's look at the first few, at least. Remember, the first partial sum is always the first term. The second term in the sequence of partial sums is the first two terms added together, which was 1 plus -1/2, which is just 1/2, and we can leave it as just 1/2. We can simplify our life there, or 0.5 if you prefer decimals. And then S sub 3 would be 1 minus 1/2 plus 1/3, and I'll just type that into my calculator and see what I end up with there, and I got 0.83 repeating. And then S sub 4 would be the sum of the first 4 terms, and I'll just use my calculator, and I got 0.583 repeating, and I'll do another one, why not? S sub 5 would be the sum of the first 5 terms, and I have that one as 0.783, and S sub 6 was 0.6167, and of course we can continue on forever. So let's think about what's happening to that sequence of partial sums. I started off with 1, and then I got 1/2, and then I got 0.8, and then I got 0.5, and then I got 0.7, and then I got 0.6. So the sequence of partial sums itself was kind of going up, down, up, down, up, down. Certainly it stayed positive in this case, but it was going up, down, up, down, up, down. I started off at 1, and then I went down to 1/2, and then 0.8, and then 0.5, and then 0.7, and then 0.6, etc., etc., etc. And you can imagine me doing that for a long time. So I've graphed over here the sequence of partial sums, not the series. Remember, this is just the sequence of partial sums. This is giving us an idea of what's happening to the series. Remember from the very beginning, the very, very beginning of 5.2, when we said that the value of the series is equal to the limit of the sequence of partial sums. That's why it's so important to look at that sequence of partial sums when we're not sure what's happening. So we can look at the limit of this sequence of partial sums. And you can see in this case, it's actually settling down. It appears to be settling down somehow. And there's a real, very logical reason as to why that is. I started off with 1. That was the first term. And then I subtracted 1/2. So I got smaller. But then I added something back to it. But the thing I added back to it was smaller than the thing I had subtracted. Okay, and then I subtract 1/4. And then I'm going to add 1/5, but that adding back the 1/5 was smaller than the thing that I had subtracted, which was the 1/4. So each one of those terms by themselves are getting smaller. So I'm going 1 and then minus 1/2, but then plus 1/3, and then minus 1/4, and then plus 1/5. Every single time you're adding something back, that was smaller than the thing that you took away to begin with. And that's this idea of this settling down, almost cyclical. It almost looks like a wave function, if you will. Okay, so that's the idea. I do want to point out, we should write this down, that without the alternating, this was problematic. without the alternating, this went from 1 to 1.5, et cetera, et cetera, et cetera, et cetera, et cetera, et cetera. It went off and off and off forever. That one diverged. So without the alternating, this particular one diverged. However, with the alternating, what happened here is I subtracted enough things from that infinitely large, that divergent series. I subtracted enough that I got converges. So the real question is how much is going to be enough, right? And that's going to be the idea. So I will maybe make a little note, just since we have it up here, that if I were to take the limit of this sequence of partial sums, it does approach something. It does settle down to, let's say, it was approximately 0.68, and you can use your calculator to continue on with that sequence of partial sums to get a general idea for it. But the point is that it converges. So the alternating harmonic series converges, whereas the regular harmonic series diverges. Okay, so now we have that pattern. We have also a test to help us out when it's not just harmonic, when it's not something that we can visualize with just plugging in some numbers. So now we have what's called the alternating series test. This is another test to help us figure out if something converges or diverges. And it's written right in the name. This only works if the series is alternating. So you cannot use this test on any other type of series. You might need to go back and use things like the divergence test instead, or the integral test, or the comparison test, or the limit comparison test. Lots of other tests that we can do. But if you have an alternating series, something that goes back and forth between positive, negative, positive, negative, positive, negative, which is oftentimes written as -1 to the power of n or -1 to the power of n plus 1, okay, then you can use this test. And what this test is, this alternating series will converge, provided both of these two things are true. Okay, and the two things are this. First of all, your next term needs to be smaller than the previous term in magnitude. So I'm only looking at, now that I know it's alternating, you look at just the terms without their negative, just the numbers themselves. Are they getting smaller? The 1, the 1/2, the 1/3, the 1/4, they were getting smaller. So that meant I went 1 and then minus 1/2 and then added 1/3 and then minus 1/4. Each time it was getting smaller, that helped settle it down. Not only did I need them to get smaller, I also needed them to get really small. So eventually I had to be adding 0, right? Eventually I had to be adding close enough to 0. They need to have a limit of the terms approach 0. Both of those have to be true at the same time. And oftentimes the way that first bullet point is written is with the word non-increasing in magnitude. So the terms the terms of the series need to be non-increasing in magnitude. And their limit has to go to 0. So both of those bullet points hold true. Then we have that alternating series converges. If one of them fails, the whole thing diverges. All right, let's practice. So let's determine whether or not the following series converge. Step 1, is it alternating? Yes, it is, because I have that -1 to the power of k plus 1. This is an alternating series, so I get to do the alternating series test. So step 2 is those 2 bullet points. So we just look at both of those bullet points. So I'm going to just list them out with bullet points just so we can get used to it. And actually, before I do that, I'm going to list those bullet points out down over here to the side. The first bullet point is they needed to be non-increasing in magnitude. Non-increasing in magnitude. So before I list out and figure that out with the numbers, another good strategy, especially when these get tricky and maybe there's a lot going on in your head, is to first plug in the numbers to just see if you see a pattern. And that's what we've been doing a whole lot. Just plug it in and see what happens. So this is the sum from k equals 1 to infinity. So I'm going to start off by just plugging in 1 and just see what happens. So if I plugged in 1, 1 plus 1 is 2. Sorry, 1 plus 1 is 2, which of course -1 squared is +1. So I ended up with 1 over 1, which is 1. Cool. Plus, and then if I plugged in 2, 2 plus 1 is 3. And so -1 cubed is definitely -1 over 2 cubed. And then plus, the next one would have been a +1 over 3 cubed, and 3 cubed, sorry, is 27. And then the next one would have been a -1 over 64, and you can imagine that forever. Okay, it's helpful to visualize that because then you can see what I mean when I say non-increasing in magnitude. The magnitude really just means absolute value. Okay, magnitude just means absolute value. Think of it like that. It really technically means distance away from zero. So if you're also taking a physics course, magnitude of a vector is the distance away from zero. So just absolute value. Absolute value. So look at the absolute value of each one of those terms. Okay, they are all non-increasing, right? If I were to look at those terms, and here's the way we write the correct notation, my A sub k, that's the in magnitude with the absolute value. Look at the formula without the alternating. Is that getting smaller? And the answer is yes, it definitely is. You can see that by looking at these terms. You could also see that by the graph. If you wanted to just graph 1 over x cubed in your graphing calculator, check. That is definitely getting smaller. That graph would have been going down. This is non-increasing, so we're good. Okay, so I know it's not getting any bigger. That's good. The second bullet point is I need to make sure it actually gets really small. So it actually has to have the limit go to 0. So the next one is I need to take the limit as k approaches infinity of that formula without the alternating piece, the in magnitude. And now this one happens to be very easy. Start off with an easy one. 1 over a really large number is 0, so ta-da. Sometimes they're going to be a little harder, and we'll do some examples. So my conclusion is, therefore, the alternating series, the sum from k equals 1 to infinity of -1 to the k plus 1 over k cubed definitely converges by the alternating series test because it passed both of those bullet points. Okay, let's do another one. Let's do another one. All right, so same thing for this next one. I'm going to start off by plugging in some numbers. I still think it's always worth it, sorry about that, to try to just plug in some numbers so you can get the hang of what's happening. A lot of it is really just add some numbers and see what happens. So I'll do that. I plug in 1 in this one right here. I have -1 to the power of 1 plus 1 is +1. If I plugged in 2, I got -1 over 2. If I plugged in 3, I got +1/3, etc., etc., etc. I just think it's visual so I can see, are those terms getting smaller? If I were to put an absolute value in front of all of them, are they getting smaller? It's a little bit more visual. Now, you could probably get away without writing out those numbers, but I think it's helpful. So let's do the 2 bullet points. So the first one is it needed to be non-increasing. Excuse me, I am a little bit sick. I'm so sorry. Non-increasing in magnitude. Sorry about that. So let's look at the terms in magnitude, meaning with their absolute value. So without the alternating piece, which in this case is 1 over k. And you can look at those numbers. 1, 1/2, 1/3, 1/4. Are they getting smaller? Cool. So check. You need the check mark, all right? Or graph it. You could have done it with a graph or list the numbers. But because I've listed the numbers, that's enough work. If you didn't list the numbers, then draw the graph. But either way, yes, it was non-increasing. And then the second one is, again, we started off with the first few easy ones. Take the limit of a sub k, so without the alternating piece, and make sure it equals 0. 1 over a large number is 0, so ta-da. So then that means that the sum from k equals 1 to infinity of -1 to the power of k plus 1 over k converges by the alternating series test. Ta-da! I do have some tea, I apologize. Okay. That's the beauty of an online class, at least. Okay, then you don't have to be right next to me while I'm sick. All right, so let's do the next one. So same thing, I'm gonna list out the first few terms and see what happens. This one might not be as obvious, but it might be depending on if you're using your calculator for it or not. There's lots of different ways. I am gonna just list out some numbers and I'm gonna use my calculator and do decimals. I think decimals might be more visual. It's gonna be personal preference. But if I plugged in 2, I ended up with +1 plus 1 over 2, which is 1.5. And then if I plugged in 3, I got a negative, and that's because it was -1 to the power of 3, in this case, would become a negative. And then 1 plus 1/3 is 1.3 bar. Okay, plus if I plugged in 4, I would have gotten a positive 1 plus 1/4, which is 1.25. And then if I plugged in, I was plugged in 2, 3, 4. If I plugged in 5, I got 1 plus 1/5, which is 1.2, 1 plus 1/6, which is 1.16, etc. I think I'm running out of space, so I'll plug in those first few terms. And then you can see, if you look at them, each term individually in magnitude, so think absolute value, each term individually is getting smaller. Okay, let's write this all down. So now the first bullet point of my alternating series test is it needed to be non-increasing in magnitude. So non-increasing in magnitude, let me look at my a sub k, which is 1 plus 1 over k. Now you might have chosen to graph that if it wasn't as obvious. Maybe you did. Maybe you didn't. I decided to look at some terms here. I also did graph it in my graphing calculator so that you can visualize it. I highly recommend that. But you can see that those are definitely getting smaller and smaller and smaller as k gets bigger. So they are definitely not increasing. Check. The second bullet point is we needed to make sure not only are they getting smaller, are they getting small enough, right? Take the limit as k goes to infinity. Now in this case, I got 1 plus 1 over a large number. The 1 over a large number goes to 0, but this guy does not. So I ended up with 1, which is not 0. So it failed. It failed the alternating series test, which means that this sum from k equals 2 to infinity of negative 1 to the k times 1 plus 1 over k diverges by the alternating series test. Okay, let's look at the next one. So the sum from k equals 1 to infinity of cosine of pi k over k squared. This one is not as obvious. It's a little bit harder to see that it's alternating, but this is why I recommend always plug in some numbers and see what happens. That's really going to be the biggest thing. Right now, I can't tell that it's alternating. I happen to know it's alternating, but maybe just looking at it, we don't know. So let's figure it out. Plug in k equals 1. Cosine of pi times 1 is cosine of pi. Cosine of pi is negative 1. So I got negative 1 over 1 squared. Plus, now I plug in k equals 2. Remember that index is a counter, so now I'm plugging in k equals 2. When I plug in k equals 2, I got cosine of 2 pi. Cosine of 2 pi is positive 1 over 2 squared. Plus, now I'm going to plug in 3. Cosine of 3 pi is negative 1. And then cosine of 4 pi is positive 1. And now you can see that in fact it is alternating. Not only is it alternating, I could actually rewrite this entire series to be something entirely different. I could say that this is the sum from k equals 1 to infinity of negative 1 to the power of k over k squared. And you can start to plug in k equals 1 into here. That would give me negative 1 over 1. If I plugged in k equals 2 into here, that would give me positive 1 over 2 squared. And you can see how those two series are the same. This now is a little bit more visually alternating because I can see that negative 1 to the k, but it is an alternating series. So now that it's alternating, let's do the 2 bullet points. The first bullet point was it needed to be non-increasing in magnitude. Let me write out the in magnitude one more time without the alternating piece. And you could graph that or list out the terms, or you can even take the first derivative, set it equal to 0, find your critical points and figure out where the function is increasing and decreasing. That was still a strategy, but this one is a little bit more obvious. It is non-increasing for sure. You can just graph it and see it's pretty obviously non-increasing. And then I would take the limit as k goes to infinity of 1 over k squared. That does equal 0, check. So therefore, the sum from k equals 1 to infinity of cosine of pi k over k squared converges by the alternating series test. Ta-da. Cool. All right, that's the alternating series test. Now we have a little bit more to think about with the alternating series. The next part is, now that we know whether or not a series converges or diverges for alternating, I want to really focus in on the convergent series. So what happens when the series converges? If it converges, I know it's going to equal a number eventually. So what number is it going to equal? That's what I really want to know, is eventually it's going to settle down. So how? Like, what is the actual sum of all of these infinitely many numbers? That's what we want to focus on. So here is a theorem about the remainder in alternating series. So I'm going to use, remainder is a common term that I'm going to use. You might think of it though as the word error, like how off I am, but really it is actually a remainder because I am human and cannot add up infinitely many numbers. But I can add up the first million. If I added up the first million, my remainder is all the rest of the stuff I didn't add up. Yeah, that's what the difference between that. That's why I call it a remainder. It's also the error when I stop adding up all of these numbers. What have I missed? That's going to be the remainder. So we're going to use capital R for remainder, and I'm going to use that capital N where N is where I chose to stop. So if I choose to add up the first 1 million terms, then capital N is 1 million. Okay, so R sub N is a remainder, and it is equal to the entire sum, all infinitely many, minus the first N terms that I already added. So this is the leftover, the stuff I didn't add up. So if I added up the first million, then the remainder is the 1,000,001 on everything else. That's what the remainder is. Okay, that's the remainder in approximating the value of a convergent alternating series by the sum of its first capital N terms. What we know, what's kind of really important, and if I were you, I would even highlight this. This is the key. The remainder satisfies the magnitude of my remainder is less than or equal to a sub n plus 1. In other words, the magnitude of the remainder is less than or equal to the magnitude of the first neglected term. This is kind of an interesting one. I really want to pause and think about this really clearly. We're going to do this example that has the numbers involved, but let me look at the alternating harmonic series one more time. So I'm going to zoom in and really look just at the alternating harmonic series, not at any of the other ones. So let me write that down. The sum from k equals 1 to infinity of -1 to the k plus 1 over k. This is the alternating harmonic series. We already earlier on in this video started plugging in numbers, so I'm not going to do it again. I'm just going to write it down. It was 1 plus -1/2 plus +1/3 plus -1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 forever. Now I knew that it converges, right? We already figured this out. We did the alternating series test. This guy converges. But what does it converge to? Like, what's it going to settle down to? I said earlier, like, I don't know, it's like about 0.6 maybe from that graph. But like, how do I know? What am I going to figure out? So what I really want to do is I want to pretend that I'm going to estimate the value of this convergent series by adding up the first 4 terms. 4 is not that great. I should probably do 1,000,000. But since I'm not going to actually add up 1,000,000 right now, we're going to have Python program figured out for us later on. But let's just imagine I did the first 4. I'm going to add up the first 4. That means that everything else is the remainder or the error. So let's look at everything else for just a second. Let's look at just everything else. Everything else, that remainder, is 1/5 minus a 6 plus a 7th minus an 8. If you look at those terms, I started off with 1/5, and then I subtracted something smaller than 1/5. And then I added something even smaller, and then I subtracted something even smaller. Doesn't really matter about anything else. No matter what all that is, it's never going to be bigger than 1/5. I never added something bigger than 1/5. So it's always going to be smaller than that first neglected term. That's what my A sub capital N plus 1 is. This is my A sub capital N. This is my A sub capital N plus 1, the first neglected term. It'll always be, no matter what I'm adding and subtracting, it's always getting smaller and smaller, so it's never going to be bigger than this. So that's the maximum my error could be. So that's what we mean by that inequality, where your remainder in magnitude is always going to be less than or equal to A sub n plus 1. The magnitude of your remainder is always less than or equal to the first neglected term. All right, let's do an example. Okay, so this example, determine how many terms of the following convergent series must be summed or added up. How many should I do? Should I do 1,000,000, 1,000,000,000, or only 4? I don't know. To make sure that my remainder is less than 10 to the negative 4. Because in reality, I'm never going to add up infinitely many numbers. But I am going to get a solid estimate, right? And probably like the first 4 decimal places is good enough. That's really what this is saying. Like maybe I only am rounding to the first 4 decimal places. So yeah, I'm off after that, but who cares? That's what this is talking about. Okay, and then although you don't need it, the exact value of the series is given. I just happen to know this was a really fun one. If you wanted to look it up, it's beyond the scope of this class, but it is really cool to figure out where the pi squared over 12 comes from. It's really fascinating. I encourage you to look it up, but totally not necessary. So let's just look at this guy right here. You can use the alternating series test on the sum from n equals 1 to infinity of -1 to the n plus 1 over n squared. It does converge. Check. How many terms should I add up to make sure that my remainder or error is less than 10 to the -4? And the nice part is it's an alternating series. So anytime it is an alternating series, I know that the absolute value of my remainder is always going to be less than or equal to the magnitude of the first neglected term. Okay, and I really want to know what that is. I really want this to be less than 10 to the -4. I want my error to be smaller than 10 to the -4. Right, I want that to be smaller than 10 to the -4. So I'm going to, in my problem, list out the formula for a sub n, which is the in magnitude, similarly to when we did that with the alternating series test. The in magnitude, if I just look at the terms themselves, we already know it's alternating. We already know that every other one is negative. And so then now I have 1 over capital N plus 1 squared is less than 10 to the -4, because this is a function notation that tells me just plug in capital N plus 1. Then you do the algebra. Now I just do the algebra. So this is going to become 1 over n plus 1 squared is less than 1 over, what is that, 10,000? 1 with 4 zeros. And then to flip the fraction, you just have to flip everything, including the direction of the inequality. Sorry, that got really sloppy. That was still a 10,000. My bad. 1, 2, 3. Not much better. I'm going to take the square root of both sides, and I got n plus 1 is bigger than 100, so n is bigger than 99. So I got that n, my capital N is bigger than 99. What does that mean? What that means is you are going to need at least more than 99, which means at least 100 terms of the series to get your remainder to be, or your error to be less than 10 to the -4. So, and this is a great example of all I need is 100 terms. Not so bad. Cool. All I needed was 100 terms. There's going to be some where maybe I need 1,000,000,000. That would be much harder to add up. Even with some computer help, right? Computers still are not perfect, and not all of us have supercomputers. We're still working towards it. We're still working towards it. All right, let's do some more. So the next one, estimate the value of this convergence series. So I'm telling you it converges. You can do the alternating series test, and I encourage that you do the alternating series test. But it's already, pretend I've already done it. This one converges. Now that it converges, I want us to actually find out what it converges to. This converges, and I want to find out what it converges to make sure that my error is less than 10 to the -3. Okay, so I'm going to start off by listing out some terms because I always think that's helpful to see what it is that we are adding up. If I plugged in 1, I got -1 over 3 cubed. If I plugged in 2, I got +1 over 5 cubed. I'm plugging it in there, 5 cubed. And then I end up with -1 over 7 cubed. And a +1 over 9 cubed, ... I ran out of space. It goes on and on and on forever. How many should I add up, right? How many should I do? Should I do the first 100 terms? Should I do the first 7? I have no idea. How many should I add up to make sure that my error is less than 10 to the -3? Well, we know that the absolute value of my remainder is less than or equal to the first neglected term. And I want that to be less than 10 to the -3. So I'm going to go back to my problem, just like I did before, and list out the formula without the alternating, which in this case is 1 over 2, k plus 1 cubed. I guess I was using k instead of n. Doesn't matter, just be consistent. And then this is going to become 1 over 2n plus 1 plus 1 cubed is less than 10 to the -3 because I replaced my k with n plus 1. Cool, and then we just do the algebra. So this will become 1 over 2n plus 2 plus 1, good, cubed is less than 1 over 10 cubed. Flip the fraction, flip everything. Don't forget to flip the inequality as well. 2n plus 3, sorry, my pen is not working super great there. Cubed, there we go, is bigger than 10 cubed. Cube root both sides. I got 2n plus 3 is bigger than 10. 2n is bigger than 7. So n is bigger than 3.5, which means you need at least 4 terms. You can't add half a term. So 3.5 needs to be bigger than. So what's the next whole number? 4. So I just need 4 terms. Actually, it's funny because the last one I needed 100. This one I only need 4. Cool. You never know until you try. So what I'm going to do now that I know I only need 4 terms, I'm going to go back and look at what I have, which is this guy, and I'm going to use only the first 4 terms. So now I know not only how many do I need, I'm going to actually add them up. 1 over 3 cubed plus 1 over 5 cubed minus 1 over 7 cubed plus 1 over 9 cubed, and I'll type that into my calculator. Negative 1 over 3 cubed plus 1 divided by 5 cubed minus 1 divided by 7 cubed plus 1 divided by 9 cubed, and I got negative 0.03058. Which also makes perfect sense that it's negative because the first term was negative. So I was adding something smaller than I had already subtracted, so it will stay negative. Ta-da! So now you know what it converges to, approximately. It's an estimate. It's not perfect because I did not actually add up infinitely many numbers, but once in a while it's cool to get a good estimate. Okay, so now we have alternating series test, the remainder in an alternating series, and now we have a couple of more definitions for alternating series. All right, so this is the last part of 5.5. Sorry, let me show that there better. Okay, assume that an infinite series converges. Okay, so we're gonna talk only about convergent series for just a second. So forget if it diverges, and you move on. You don't even look back. But if it does converge, how does it converge? The series converges absolutely if the series with the absolute value also converges. Otherwise, the series is said to converge conditionally. The best way to think about that is with the alternating harmonic series. So the regular harmonic series, the sum from k equals 1 to infinity, diverges. We already knew that from the integral test a long time ago. But we also learned in this video that the sum from k equals 1 to infinity of negative 1 to the k plus 1 over k converges. We did that with the alternating series test. So it converged, but only barely. Right? Because without that negative, it would have diverged. So it only barely converged. Or really a better way to say that, it was conditional. It was conditional upon that negative. Without the alternating, it would have diverges, which means we say that it converges conditionally. If they both converged, then we say that it converges absolutely, meaning it converged with or without the negative. Okay, and then there is a nice little theorem, absolute convergence implies convergence. So if something is absolutely convergent, then it converges with or without the negative. That's, I feel like, an obvious theorem, but there it is, with or without the theorem, the negative. All right, let's just do an example. So I'm going to leave that up there, but let's do that first example to try to visualize what's going to happen. There is multiple ways that you can go about thinking about this convergence conditionally or absolutely. There's definitely more than one way. So be careful with it. Make sure we can think it through. The sum from n equals 1 to infinity of negative 1 to the n plus 1 over n to the 3/2. My recommendation is always to start off with this first step, which is to look at the exact same series, but without the negative. That's my recommendation as your step number 1. You might choose to do the alternating series test as your step number 1. That's not wrong, but this is my recommendation because it'll always be a little bit faster this way. There's more than one way to look at this. So I'm going to look at my series without the alternating. And now it has nothing to do with an alternating. You cannot do the alternating series test for this one. So you now go back to everything you've already learned so far. Maybe I'm going to do the divergence test, the integral test, a p-series test, a comparison test, anything you've learned up until now, or even that you're about to learn in the next section. We got to figure out if this guy converges or diverges. Okay, so this particular one's nice and easy because I started easy. I'm going to look at this guy. This one is a p-series. This one is a p-series with p equals 3/2. Therefore, this one, let me write my therefore in the correct spot. Therefore, this one converges. Cool. Converges by the p-series. Cool. And then your step 2 would be to decide, do I now need to do the alternating series test? So I'm going to put it down as a question. Do I need the alternating series test? Sometimes you do, sometimes you don't. Now, if you are not sure, just do the alternating series test. Super easy to do. It's not hard. You can always just do the alternating series test for step 2. Every time, that'll be just fine. It really will. But I like to maybe think about it, because did I even need it? Well, without the negative, it converges. So what do you think? What's going to happen if I throw in the negative? Isn't it just going to get smaller? If I start subtracting something from finite number, isn't it just going to get smaller? Which of course still converges. So in this case, do I need the alternating series test? No, because I already know that without the negative, it converges. So throwing in the negative, it will also converge. That's this theorem right here. It will also converge. So that means they both converged. And instead, my final answer is the sum from n equals 1 to infinity of -1 to the n plus 1 over n to the 3/2 converges absolutely. It converged with and without the negative. When it converges without the negative, it will of course converge with the negative, so you don't need the alternating series test. No, it is totally fine if you just did the alternating series test. If you just said yes to this and did the alternating series test, it would have been converges. And then if they're both convergent, then it converges absolutely. So same amount, same final answer. Totally fine. Okay, let's do another one. It's not easy. I know it's definitely not easy. Let's do another one. Same thing, part B. I'm going to do the exact same 2 steps because I think that'll keep us in line. So step 1 is to first look at, I'm going to separate this on the screen there. I am going to look at the series without the negative. So the sum from n equals 2 to infinity of 1 over the square root of n. And then ask myself if this converges or diverges. Without the alternating. I'm not using the alternating series test right now. I might later, but not right now. So this is just a p-series, or maybe you do an integral test, or maybe you do a divergence test, or maybe you do all kinds of whatever other stuff that you might be doing. But this one is a p-series, so I'm going to start off with the easy ones, where p is 1/2, which is less than 1. So that means that this series diverges. This series, the non-alternating version, diverges. So now I'm on to step number 2. And step number 2 is to ask yourself the question, do I need the alternating series test? The answer is yes, I do. I very, very much need it because without the negative, it diverges. So now I don't know, like if I add in the negative, it's going to be smaller than infinity. I don't know what that is. What's smaller than infinity? I have no idea. It might be infinity. It might be 12. Like it's not enough information. So I need the alternating series test here, which is why maybe you just do the alternating series test every time, because sometimes you need it, sometimes you don't. So maybe just do it every time to be safe. But here I definitely need the alternating series test. So the alternating series test is to first decide if the terms are non-increasing in magnitude. You can list out the terms. It would be 1 over the square root of 2, then 1 over the square root of 3, then 1 over the square root of 4, 1 over the square root of 5. Maybe you plug those into your calculator to get some decimals. Maybe you look at the graph. Either way, it's not increasing, it is. And then the second part of that bullet point, is to take the limit as n goes to infinity of 1 over n to the 1/2. 1 over a large number goes to 0, ta-da. So that means it converges. Good. So now I know that with the alternating, it converges. So let's write out that conclusion. That means that with the alternating, the sum from n equals 2 to infinity of -1 to the n over the square root of n converges by the alternating series test. But it diverged without the negative, which means that this converges conditionally. It only barely converged. Only barely. I don't know if that's really the right mathematical term, but that's the way you can think about it. It only barely converges. Or conditionally. It was conditional upon that alternating piece. Cool. All right, let's do another one. Same 2 steps. I really am going to do those exact same 2 steps every single time. So let's look at this one and we start off with step number 1. Step number 1 is to look at the series without the alternating. So here I have the sum from n equals 1 to infinity of -1 to the n over n to the 7th. So let me look at the sum from n equals 1 to infinity of 1 over n to the 7th. Is this one convergent or divergent? You go back to everything that you learned before, comparison test, integral tests, etc. This one is another p-series. We've got some boring ones. That's okay. We've got a p-series here where p is 7, so this one converges. Ta-da. So then I move on to step number 2, and step number 2 is, do I need the alternating series test? Well, here, no, I don't. I don't need it. You can always use it though. So if you want to use it, you'll be just fine. I don't need it because without the negative, it converges. So with the negative, it would have just gotten smaller, which means it still converges, which means they both converged, which means that the sum from n equals 1 to infinity of -1 to the n over n to the 7th converges absolutely. Ta-da. Ta-da. Let's do another one, okay? Same couple of steps. They're all very, very similar. The more we practice, the easier it's going to be. Let's look at the next one. The sum from n equals 1 to infinity of -1 to the n times 3n plus 1 over 4n minus 7. Same kind of idea. Step 1. Let's start at the beginning. Step 1 is to look at it without the negative. I'm going to look at a completely different series, the sum from n equals 1 to infinity of 3n plus 1 over 4n minus 7. Here's a good one because it's finally not a p-series. We've been doing too many p-series. They're not all p-series. Here is one that's not. So I do want to think about all of the other tests that I have to figure out if this one converges or diverges. The first test that we learned was called the divergence test. And remember, the divergence test doesn't always work. Sometimes it was inconclusive, so we have to be careful with that. There was also the integral test or the comparison test or the limit comparison test. The integral test I don't really want to do because that doesn't look like fun to do an antiderivative of, and that's okay. I'm going to think about the divergence test, but remember the divergence test doesn't always work. So let's think about it. The divergence test was take the limit as it is and see what happens. And if the limit was 0, then too bad, inconclusive, move on, try a different test. If the limit was not 0, then it diverged. You never got the answer of convergent when you did the divergence test. So let's do that. Look at that. I can do that limit in my head. I can do L'Hopital's rule in my head. I got 3 over 4. That's not 0. This diverges. So let's write that down, all right? So I'm going to do the limit as n goes to infinity of 3n plus 1 over 4n minus 7. I do L'Hopital's rule in my head. I got 3/4, which is not 0, which means the sum from n equals 1 to infinity of 3n plus 1 over 4n minus 7 diverges by the divergence test. Okay, so let's see if it converges with the alternating. Sometimes it works out that way, sometimes it doesn't. Obviously, let's look at step 2. Step 2 was, do I need the alternating series test? Well, yeah, I got diverges, so maybe, just maybe, it converges if I throw in the negative. So let's do the alternating series test. So let's say yes, let's do the alternating series test. A sub k, or I guess A sub n in this case, was 3n plus 1 over 4n minus 7. And is that non-increasing in magnitude? You can graph it if you'd like. Take the limit as n goes to infinity of 3n plus 1 over 4n minus 7. Did it equal 0? No. So it failed the alternating series test. I'm going to give myself a little, sorry about that. I'm going to give myself a little bit of space if I can try to, sorry about that. All right. It failed. There we go. Maybe, there we go. It failed both step 1 and step 2. So that means the entire thing diverges. Sorry about that. That just means that the sum from n equals 1 to infinity of negative 1 to the n, 3n plus 1 over 4n minus 7 just simply diverges. It doesn't converge conditionally or absolutely. It just diverges because it failed the alternating series test and also without the alternating piece. So they both diverge, it diverges. Cool, let's do another one. Yeah, all right, let's do another one. You might realize that I didn't need the alternating series test. You might realize that because if it diverges by the divergence test, that means that it automatically fails the alternating series test because those two are the same. So you might realize that if I were using the integral test maybe or p-series test, I don't know, I would still need this. That's why it's worth always doing both just to be safe. Okay, let's just do one more. We're on a roll. It's always worth it to have a little bit of extra practice here. Same idea. First, I'm going to step number 1, look at the series without the alternating, and you're going to realize that this one diverges by the p-series test. And so then if I were to do the alternating series, I would have to do the alternating series test. I would notice that a sub n is 1 over the cubed root of n is definitely non-increasing for sure. And you would notice that the limit as n goes to infinity of 1 over the cubed root of n also goes to 0 for sure. So it diverged without the negative, but it passed the alternating series test, which means that that series, the sum from n equals 1 to infinity of negative 1 to the n over the cubed root of n, it did converge because it passed the alternating series test, but conditionally because it diverged without the alternating. Ta-da! All right, that's all there is for alternating a series tests. Thank you.